We will investigate the Weierstrass function. So this is the function f of x given as this sum, k from 0 to infinity, cosine by a to the kx over b to the k. B is a real number strictly greater than 1. A is a positive integer that is odd. A is greater than b. In fact, a is greater than b multiplied by 1 plus 3 pi over 2. What is weird or interesting about this function, f of x, is that it is uniformly continuous over the set of real numbers, but it is nowhere differentiable. So if we try to compute the derivative of this function f of x at x0, we can, for example, compute the quantity f of x plus h minus, or x0 plus h minus f of x0 divided by h, and then investigate the limit as h goes to 0. If this limit exists as a finite real number when we take the limit as h goes to 0, then basically the function is differentiable at x naught. So we'll show that basically the magnitude of this function at any x naught for this given function, the magnitude goes to infinity, which means that at no real number this function is differentiable. Let's focus initially on the fact that f of x is uniformly continuous. So we will start by showing that the cosine function is uniformly continuous. Note that f of x is the sum of cosines. Now we will make use of this inequality that the absolute value of sine x is less than or equal to the absolute value of x, and this is true for every x that is in R. Because we know that the absolute value of sine x is less than or equal to 1. So this inequality is clear whenever the absolute value of x is greater than or equal to 1. We know that sine x is an odd function, and x is an odd function. We can just focus on positive x, and specifically on positive x from 0 to 1 or 0 to pi over 2. That's, so x is an angle in the first quadrant. So we can basically show this inequality geometrically by drawing a part of a circle that has a radius of unity. And this is point A. So this is our 0, 0. And this is angle x. And so this is sine x. And from here to here, this is cosine x. So the coordinates of point C are cosine x and sine x. Now, triangle ABC, it has this height, which is sine x, and the length of the base, which is the length of line segment AB, is 1. So the area of triangle ABC is 1/2 times the height, which is sine x, times the length of the base, which is unity. So the area is 1/2 sine x. The area of triangle ABC is upper bounded by the area of this shaded sector here. So what is the area of this shaded part? It is pi times the radius squared, which is 1. And then we need to multiply by the fraction, which is x divided by 2 pi. Pi goes with pi, and then we have also x over 2. So we have sine x over 2 is less than or equal to x over 2. And hence, we have sine x less than or equal to x. And from here, we go to that the absolute value of sine x is less than or equal to the absolute value of x. True, this is true for every real x. Okay, so going back here, if we investigate the difference between these two cosines, we can express the difference cosine x minus cosine y as minus 2 sine x plus y over 2 sine x minus y over 2. And then we can upper bound the magnitude of this sign by unity, by 1. And then we can upper bound the magnitude of sine x minus y over 2 by the magnitude of x minus y over 2. And so we have that the magnitude of cosine x minus cosine y is less than or equal to the magnitude of x minus y. Of course, we can, exploit the differentiability of cosine x. So if we take this for granted that cosine x is a differentiable function, then we can arrive at this inequality using the mean value theorem. So by the mean value theorem, suppose that we take here, x strictly less than y. By the mean value theorem, cosine x minus cosine y over x minus y is equal to the derivative of the cosine function evaluated at some point between x and y. So the derivative is minus sine, and let's say that we will evaluate at zeta, where zeta is a number between x and y. Now, if we take the magnitude of both sides, so this will be magnitude sine zeta, and this is less than or equal to 1. So, so this inequality is true for every x that is not equal to y, and so you can multiply basically or move this to the other side, and then if x is equal to y, then we have the inequality 0 less than or equal to 0, which is valid, which means that this is always true. Now, why I'm saying that the cosine is uniformly continuous, why actually this inequality tells us that the cosine function, cosine x, is uniformly continuous. This is because I can make this distance, this absolute value, as small as needed by basically picking a real valued x and a real valued y that are separated by less than some delta. And so, in fact, in our case here, choosing delta to be, choosing this distance between x and y to be less than epsilon, we are able to make the absolute value of cosine x minus cosine y less than epsilon. Okay, so for every epsilon that is greater than 0, we can find the delta. And here, delta in this particular problem, we can choose delta to be exactly equal to epsilon, such that if we choose an x and y with, that are separated by no more than, but by less than delta, by strictly less than delta, which is epsilon in our case here, then because of this inequality, the absolute value of cosine x minus cosine y will be less than epsilon. Now, because our choice of delta depends only on epsilon and not on x or on y, then the function, this is basically the definition of uniform continuity. Now, we will try to basically do something similar, but for f of x itself. Not just for a term, but we want to show that f of x itself, which is this infinite sum, is uniformly continuous. So we will define this f n of x, and this is basically like f of x, but it is a truncated sum where the index of summation k goes from 0 to small n. Our interest now is to show that we, by choosing x and y close enough, we are able to make this absolute value less than any arbitrary positive number epsilon. The trick is that we will insert minus fn of x plus fn of x minus fn of y plus fn of y, where these again are the truncated sums. And then we will apply the triangle inequality. So basically, the magnitude of the sum of these three quantities is less than or equal to the sum of the magnitudes. And then what we'll do is that we will try to make each one of those terms less than epsilon over 3. And by doing this, this absolute value of f of x minus f of y can be made less than epsilon by, again, choosing x and y to be close enough. So let's focus on this middle term here. Now this middle term, so let's express fn of fnx and fny using the truncated sums. Apply the triangle inequality. So by the triangle inequality, the magnitude of the sum is less than or equal to the sum of the magnitudes. B is a real number that is strictly greater than 1, so it is positive. We can take it outside the magnitude, and then we have to handle this magnitude inside the sum. Now, remember that we have this inequality from the very beginning, which is that the magnitude of cosine x minus cosine y is less than or equal to the magnitude of x minus y. So this is exactly what we can do here. I can take this magnitude and say that this is our bounded by the magnitude of by a to the kx minus by a to the ky. And a is a positive number. It is indeed an odd integer greater than b. Then we can actually take pi a to the k as a common factor, and then we have this is the absolute value of x minus y. So suppose that we will choose x minus x and y such that their distance is upper bounded by epsilon over 3. So epsilon is this positive number times b over a to the power n times 1 over pi n plus 1. Note that if the absolute value of x minus y is upper bounded by this quantity, and since we have a is greater than b, so this b over a is a number that is less than 1. And here we are raising it to the power n. So for k that is less than or equal to n, b over a to the power k is greater than or equal to b over a. And so this quantity here is upper bounded by epsilon over 3 b over a to the power k by 1 times 1 over pi. And then here in the denominator, we also have n plus 1, and we will see its role shortly. So this means that, again, if we have this difference of the two cosines, then it is upper bounded by pi a to the k, and then we have the absolute value of x minus y, which by design, we will have this thing less than by a. So this is copy and paste, take this here, and then now by design, this will be less than that, and so it is less than epsilon over 3 e to the k over a to the k 1 over pi, and then we have here n plus 1. So we have pi, we have a to the k, and so this is epsilon over 3 b to the k over n plus 1. So this means that each term in this summation here, which is the absolute value of the difference between the two cosines divided by b to the k, each term here is upper bounded by epsilon over 3n plus 1. And we have a summation, and this summation has exactly n plus 1 terms because we have the index k going from 0 to n. So this overall sub is upper bounded by epsilon over 3. So this middle term is upper bounded by epsilon over 3. Now let's investigate this or that term. They are the same. So now we have the difference between f of x, which is the summation k going from 0 to infinity. This is a truncated sum k going from 0 to n. So the difference will be a summation that where the index of summation k goes from n plus 1 to infinity. Now, going from here to here, let's do it in slow motion. So first apply the triangle inequality. So by the triangle inequality, the magnitude of the sum is less than the sum of magnitudes. And here we have cosine by a to the k x over b to the k. Now, we also know that the magnitude of the cosine is less than 1, is less than or equal to 1. And so we can upper bound this summation by this summation here, which is a geometric series. And so we can sum it, and basically b is a given parameter. It is a parameter of the function f of x. We can choose n large enough such that we make this quantity less than epsilon over 3. Note that manipulating this term is can be done similarly. As you can see from here, the dependence on x actually disappears because in this upper bounding step, we take cosine by a to the k x, and it is upper bounded by 1. So when we do this upper bounding, basically the parameter a will disappear and also x will disappear. So replacing x by y will not change the argument that is here. Okay. So now each of those terms can be made less than epsilon over 3. So by choosing x and y to be close enough, then we are able to make this absolute value of f of x minus f of y less than any arbitrary positive number epsilon. This is exactly the definition of uniform continuity, so long as the delta, basically the upper bound on the distance between x and y, neither depends on x nor on y. Okay, so in summary, here is the proof of the uniform continuity of the function f of x for every epsilon that is greater than 0. For every epsilon that is greater than 0. What we can do is that we can choose an n that is large enough. We can choose a value of small n that is large enough. And this value of n will depend on the parameter b, which is a given parameter in function f of x, and also on the epsilon we are investigating. So we can choose an n that is large enough, and then we can insert f n of x, f n of y here. Now, by choosing n to be large enough, and based on this argument, we are able to make this go below epsilon over 3, and also this go below epsilon over 3. Now, the challenge to finish this off, we will need to handle the middle term. So now, given n, so n that is large enough so that these two guys get less than epsilon over 3, now we are in a position to make this less than epsilon over 3. How can we do it? So we have n now, we have n, and we can do it by choosing x and y that are that are sufficiently close to one another. Specifically, we will choose x and y to satisfy that the absolute value of x minus y is less than epsilon. So basically, so this is our delta. So it depends on epsilon. It depends on those parameters b and a, and it depends on n. Well, n itself again is chosen based on epsilon and b. Okay, so we have a delta that will depend on these two parameters a and b and on epsilon. Delta will not depend on the exact choice of x and the exact choice of y. So long as the separation between x and y, or the distance between x and y, is less than this quantity, then we are able to make this middle term less than epsilon over 3. So basically, for every epsilon greater than 0, we, and for every x and y satisfying that the absolute value of x minus y is less than a delta that does not depend except on epsilon and the parameters a and b, we are able to make this thing, arbitrarily small, less than any positive epsilon of our choice. So that's uniform continuity. Now, basically the thing about this pathological function f of x is to show that it is nowhere differentiable. And so the idea is we want to show that a quantity, this quantity here, so R is any given real number, and h of m is a carefully designed positive sequence. So this is basically it's indexed by the integer, the positive integer m. It is positive, and h of m tends to 0 as m tends to infinity. So we have this quantity f of r plus h of m minus f of r over h of m. If there is a first derivative, if the first derivative exists, what should happen? When you take the limit as m goes to infinity, then h of m will go to 0. And if h of m go to 0, then this quantity here, if the first derivative exists, must converge to a finite real number. So we will actually show that the magnitude of this quantity tends to plus infinity as m tends to plus infinity. And this will be the case regardless of our choice of the real number r, which means that actually our function is nowhere differentiable, despite the fact of being uniformly continuous over the set of real numbers r. We will take this quantity and recall that f of x is summation k from 0 to infinity and then we have cosine by a to the kx over b to the k. And so just replace x by r plus h m, and then replace x by r. So this is exactly what to go from here to there. And then what we'll do is that we will split this into a summation from 0 to m minus 1, and a summation from m to infinity. And then we will take this summation here and move it to the other side. Okay, so now we have the summation from m to infinity is this quantity minus the summation from 0 to m minus 1, and then we will take the magnitude of both sides. Now we will focus on this, and we will try to obtain an upper bound. So first order of business is just to apply the triangle inequality. So the magnitude of this difference will be less than or equal to the magnitude of this quantity plus the magnitude of the sum. And by the triangle inequality, also the magnitude of the sum is less than or equal to the sum of magnitudes. Now we can use our initial inequality here and apply it there. So basically, this difference of the two cosines in magnitude will be less than, we take the difference, so pi a k r plus hm minus pi a to the power kr, and so this will be pi a to the k hm, and everything here is positive, and so basically the upper bound here is this quantity. hm will go with hm, and then we have and pi is a constant that can be taken outside, and we have a geometric series. Now it is a finite geometric series with the ratio a over b, and so we can sum this geometric series, and in the sum we get the term a over b to the power the number of terms, and we have m terms in this summation minus 1. One further step of our bounding is that we can say that this quantity here is less than, without the minus 1. And so this part is upper bounded by this absolute value plus pi over a over b minus 1. We obtain this by obtaining the geometric series, and then we have a over b to the power m. Now we need to focus on this term here, and we will actually try to lower bound it. And in doing so, we need now to know what h of m is. Okay, so when we did this upper bounding, what happened is that h of m disappeared from here, but now we will need to basically design this positive sequence that converges to 0 as m tends to infinity. And so the idea that this is the real line, and the real line, it has integers on it. Okay, and so what you will do is that you'll take your number r. This is the real number of interest. It's an arbitrary real number, and then you will take ar, and then you have a squared r, a cubed r, and so those are numbers. One of them is a to the mr, and what you do is that you see where is a to the power mr is on the real. Let's suppose that it is here. Okay, then alpha m is the integer that is closest to this number a to the mr. Okay, which means that a to the mr will be lower bounded by this integer alpha m, the closest integer, alpha m minus half, and upper bounded by alpha m plus half. Okay, this means that we can write down a to the power mr as alpha m, which is this closed integer, plus a difference or a discrepancy between these two guys, and this difference is a number living basically between minus half and half. If we multiply those two inequalities by minus 1, we get 1/2 greater than minus epsilon sub m greater than or equal to minus 1/2. Then we can add 1 to all sides, and then we get this quantity here. Note that 1 minus epsilon m is strictly positive. It is a quantity that is living between 1/2 and 3/2. And h of m will be taken to be this 1 minus epsilon m divided by a to the power m. Note that a, this is our friend from the beginning. This is one of the two. A and b are the parameters of f of x. And a is this parameter that must be chosen to be an odd integer, and it will become clear shortly why this should be the case. Okay. So am h of m is, so am a to the power m h of m is 1 minus epsilon m. Now we want to lower bound this, so let's basically handle each of those cosines. So this is cosine by a to the k r plus a. Note that we are basically simplifying those cosines inside the summation, and this summation is from m to infinity. So k is greater than or equal to m. So the trick here is that we'll take this a to the power k and we'll write it as a to the power k minus m, which is non-negative, and then a to the m. And then we will take a to the m inside this bracket. A to the m times r, this is the quantity that is expressed as alpha m, which is the closest integer, plus this number that lives between minus half and half. Okay, so a to the m with the r will give us alpha m plus epsilon m. And then we have a to the m h m, and this is by design 1 minus epsilon m. And so this guy will go with this guy, and we have cosine pi, and then we have a to the power k minus m, and so we have this odd integer, okay, and then alpha m is an integer plus 1, it's also an integer, so we have cosine pi and then an integer. Now this is interesting because alpha is an integer and a is an integer. This means that this cosine is either plus 1 or minus 1, depending on whether the integer is odd or even. Now a is fixed as an odd integer, so a is odd. So now what we have is cosine by a to the k minus m and then alpha m plus 1, like this. Now this is always odd. So if alpha m plus 1 is an even integer, then even times odd is even, and cosine pi times an odd times an even integer is 1. Okay, so we will get 1 if alpha m plus 1 is even. Now, if alpha m plus 1 is odd, then an odd integer times an odd integer is odd, and cosine pi times an odd integer, this is minus 1. Alpha m plus 1 is odd. Okay, and so we can combine these two cases and say that this cosine is simply minus 1 to the power alpha m plus 1. Now, the other cosine, we can repeat the same trick. So again, we can split this a to the k as a to the k minus m times a to the m, and then a to the m can be combined with this r to give alpha m plus epsilon m. Note again, alpha m is an integer, and epsilon m is a real number that is between minus half and half. Now we have cosine, of a sum. So it is cosine of this first term, cosine the second term, minus, sine. Note that one term here will be sine pi a to the k minus m and then alpha m. For a sine pi times an integer is always equal to 0. So we don't really need to care about the product of these two signs. And what about here? Now for this cosine, we also are in a situation in which we have cosine pi times an integer. Cosine pi times an integer. Since we are fixing a as an odd integer, then the fate of this cosine is basically depends on alpha m. If alpha n is even, this cosine is 1. If alpha m is odd, then this cosine is minus 1. And so the other cosine, we will just leave it as is, and then we have minus 1 to the power alpha. Now we have the difference between these two guys. So one of them is equal to minus 1 to the alpha m plus 1 minus, and then this other guy is minus 1 to the power alpha m, and then we have cosine pi a to the k minus m epsilon m. And so we have here minus, so this is like minus 1 times minus 1 to the alpha m, so I can change this to a plus and have this as plus 1. Then we can take minus 1 to the alpha m plus 1 as a common factor, and we are left with 1 plus cosine pi a to the k minus m epsilon m, like this. Now this term here does not depend on the index of summation. So we can take it outside, and because we have this magnitude or absolute value, the absolute value of plus and minus 1 is just 1. And so this term will disappear, and we just have those. Now the cosine is between minus 1 and 1. Okay, so cosine of by a k minus m epsilon m, this is always greater than or equal to minus 1. Adding 1 to both sides, so 1 plus cosine by a to the k minus m epsilon m. So this is greater than or equal to 0. And the sequence is positive. This hm is positive, and b is a real number greater than 1. So basically, these are non-negative terms. This is a sum of non-negative terms, and the sum itself will be non-negative. So actually, we don't need to put the absolute value, okay, because we have non-negative terms. Moreover, if you have a sum of non-negative terms, so the sum of non-negative terms is always lower bounded by one of them, one term. And here we will pick the term. So this is the term with the summation index k that is equal to m. So because this is again is a summation of non-negative terms, it is lower bounded by 1 plus cosine, and then we'll put k equal to m. So we'll have a to the 0, which is 1. So 1 plus cosine by epsilon m, and then we have in the denominator we have hm b to the power k. Okay. Now note that epsilon m is between minus half and half. Okay. So this is again this is by design. Okay. And then we multiply by. So the argument of this cosine is between minus pi over 2 and pi over 2. So this means that the cosine is non-negative. So this cosine is non-negative. So cosine by m, cosine by times epsilon m, because by epsilon m is between minus pi over 2 and pi over 2, then this is a non-negative cosine. And so if we add 1, then this is always greater than or equal to 1. And so we can lower bound this term here by 1. So we obtain 1 over hm b to the power m. So the last step is to lower bound 1 over hm using the formula for hm. So basically am hm a to the power m hm, this is 1 minus epsilon m, which is living between 1/2 and 3/2. Take the reciprocal of all sides, okay, and then let's focus on this part because we are interested in a lower bound. So multiply both sides by a to the power m. So it must be the case that 1 over hm is greater than 2/3 of a to the power m. And so we will have here a lower bound, and this lower bound is only in terms of these two parameters, a and b. Okay. So now what we did, I mean, to basically see what exactly we did. So we took this summation. So this is a summation from m to infinity. So this is equal to this term here, which is a summation from 0 to infinity minus the summation with the index k going from 0 to m minus 1. We upper bounded this guy. So the upper bound, this involved basically the use of the triangle inequality, then the use of this thing that absolute cosine x minus cosine y is less than or equal to absolute value of x minus y. Then we obtained a geometric series, and then we removed this minus 1. So we obtained an upper bound on this term here, and this is the upper bound. Then we shifted our focus on lower bounding this guy, okay, and we obtained the lower bound, which is 2/3 a over b to the power m. Okay, and so now we say that basically this absolute value plus this term here, this is greater than or equal to this. I can just take this term and move it to the other side. Okay, so we will have now that this absolute value is greater than or equal to 2/3 of a over b to the power m minus this term. Take a over b to the power m as a common factor, and this is multiplied by a number. Now, if this number is 0, or if this number is negative, this is very uninteresting, because we know that the absolute value is greater than or equal to 0. Can we make this number strictly positive? Yes, we can, by a proper choice of the two parameters a and b. So actually this will impose a certain relationship between a and b, as we have seen in the beginning when we defined the function f of x. Okay, so can I make this thing strictly positive? Yes, if 2/3 is strictly greater than pi over a over b minus 1. And solving for this, we need, for this term to be strictly positive, we need a over b to be strictly greater than 1 plus 3 pi over 2. And so that's the mysterious condition at the very beginning. So we need to choose b to be greater than 1. Why? So let's now understand why actually we have these conditions. So while studying the uniform continuity of the function f of x, so we have this upper bound, and this upper bound involves 1 over b to the power k. So this is a geometric series. This is an infinite geometric series, and its ratio is 1 over b. So to be convergent, so that we can make this number less than epsilon over 3, it must be the case that 1 over b is strictly less than 1. So b must be strictly greater than 1. Now for a must be an odd integer. So this allowed us actually to manipulate those cosines and simplify them in this form. So this required that a to be not just an integer, but also an odd integer. But now we see that to have a meaningful inequality here, this constant must be strictly positive, and this will require that a is greater than b multiplied by 1 plus 3 pi over 2. If this is the case, then this is a strictly positive number, and it is multiplied by a over b to the power m, and this is strictly greater than 1. So now we can see that if we try to take the limit as m tends to infinity, and hm will go to 0. So this, if there is a a first derivative, this should go to a finite real number. But now this will not happen, because this quantity is lower bounded by a positive parameter times a number that is strictly greater than 1 raised to the power m. So this thing actually will increase exponentially. So this means that the limit of this absolute value is actually plus infinity. And this is true for every small r. So small r was an arbitrary real number. So indeed, our function f of x is nowhere differentiable.